Okay.
So yeah, we are recording now.
Cool. Good afternoon, everyone. So what I want to do today, well, first of all, if there's any question or something that you would like to ask or comment about the previous session, or
Your opinion of Deepseek, Professor?
my opinion of this Deepseek.
Yes.
Yeah. Firstly, I lost you. Where am I? I lost my screen. Let me. I haven't used it enough, like to have an informed opinion. To be honest, I just play with it a little bit, and then I try again yesterday, and I couldn't access it, so I don't know if there's an issue or whatever. And I haven't downloaded the modules. That's what I wanted this weekend, hopefully, and read the paper because what I find quite interesting, I think, is the way they train the model, so that apparently it's that cheap. Having said that, I am not totally convinced that it is what people or what they claim it is. Like I don't know. Why the class English? That is something that you would have to ask Gretel. Yeah. I don't know. I was told the class was going to be in English when I was asked to teach this class.
Yeah.
So basically, so yeah, but that's something that you would have to take to Gretel. Gretel was the one, the director of the program was the one that told me at least that it was going to be in English. So what I was saying about Deepseek is that I'm not a total believer of what they claim. I do believe that they train it better than what we have seen so far with OpenAI and so on. Like the training was cheaper, but I also don't think it's like I mean, it's remarkable. I'm not saying it's not. I'm just I don't know. I need to check it better to see if I'm gonna buy into the hype that is going on. That's what I'm trying to say. So I hope to use it this weekend and read the paper because I haven't read it, to be honest. I understand that they did a lot of reinforcement learning on the training. So, but I'm not sure if it was reinforcement learning if it's between if it is within the how is it called, reinforcement learning with human feedback, which is the way that RL is implemented in the previous models, like OpenAI models, or they did something different, more like actual reinforcement learning, because I mean, there might be controversies or there might be people arguing that the way RL HF is not actual reinforcement learning. But yeah, I don't know. I would need to read the paper a little bit and have a better opinion. So far, I don't buy the hype that is like everything that is going on. I mean, like it's remarkable, but I don't think it's that like for instance, Nvidia stocks, like they took a dip, but I'm pretty sure they are going to go again. I mean, again up. I mean, they took a dip of they were saying like 16, 17%, and that's a lot. I mean, yeah, it's a lot. I mean, but they were 133 over the last year. I mean, that was the gain they had from over the last year, I think, over 100%. So 16% dip is more like a correction than actually going down. That's the way I feel. I don't know. Yeah, the way I see Nvidia shares is like they are on sale, so it's yeah. Yeah, also, I mean, coming from China, well, I always have a little bit of a skepticism about that. So yeah. But I think, anyway, I mean, even with all that, I think the achievement is quite remarkable. I mean, because even if they, it's just that when you say, okay, it's only $5 million to train the model, sounds like only $5 million. But yeah, it's not too bad compared to the amount of money people are using. But then all the other like, oh yeah, and OpenAI is using $500 billion now. Well, they are supposed to with all that is going on, but I mean, and also I think the investment of that Deepseek has done in GPUs over the years since its foundation is quite high. I was reading something about it, so yeah, I think it's remarkable, but I don't buy all that amazing hype that is going on, and even today I saw OpenAI, no, like artificial intelligence was going to take our jobs, but actually is AI taking OpenAI's jobs, and it's like, really? I mean, I don't know anyone who has stopped totally using ChatGPT or GPT, whatever the version is now, 4.0 or whatever. I mean, because of DeepSeek, to be honest. I mean, some people might have. I mean, but as far as I know, most people that I know use ChatGPT are still using ChatGPT. Probably not as often. Probably now they are combining, which is good. So yeah, I don't know. That's my opinion. Don't believe me. I mean, just.
And what about the open source? It's like the open source. Do you have any initial thoughts about it, or what are your thoughts about
I
that?
need to see if it is actually open source or is the same approach that Meta was using with Llama. Because for instance, Llama is often called as an open source model that you can run. I mean, and it is open. There is also controversy around that because some people claim that it's not totally open source because you don't know neither the data it was trained on, you don't know the code, you don't have access to the code, to the source code. You only have access to the weights. And you can actually fine-tune the weights to your application, which is very nice. It is something really nice to have, and you can have it locally, and then you can use it for whatever purpose you want locally, which is remarkable. But it's not fully open source. Many people call Llama, for instance, open weight. No, open weights, not totally open source. So I'm not sure if DeepSeek is exactly the same. I don't know if you have access to the code and the data they use to train, and that particularly those two. But as far as I understand, it might be the same as Llama. I don't know if any of you know if you can access the code and the data they use to train it. Because if you can't, then it's the same as Llama and it's more like open weights. But once again, I haven't checked like closely if it is indeed open source or it's just open weight. I mean, open weights is still remarkable. The fact that you can download it and run it and have had similar performance to that of OpenAI models, that's remarkable. I mean, that I'm not disputing. That's amazing. Right? Still, yeah. Yeah, I hope NVIDIA shares rise up again. Someone has NVIDIA shares, I guess. I think they are going to rise again. So I don't know what they were like 2,500 today, $2,500 or something. Which is still. Oh, sorry, 2,500 pesos is not dollars. So I don't know if there's anything else.
Professor, I do have a question.
Yes, you don't have a
Are
question.
there-
Oh, what?
It's not related to DeepSeek.
Okay.
It's my question is if there is any techniques to analyze weights and biases of a trained model to get valuable insights and actionable items.
Yeah, it is funny. You can use weight and biases actually. I don't know if you're familiar. There is a service, actually, a company called Weight and Biases. And actually it's precisely for that. So I don't know if you're aware of weight and biases.
No, I'm not aware of it.
Yeah, it's a company. They have the website is Weight and Biases, and if you Google it and do it, you can actually do a lot of analysis of your model insights. I mean, it allows you to do, particularly more than weights, it allows you a lot of analysis of hyperparameters. I think it's a really good tool. Like you can schedule the way you're going to be training your model. So that would be one way to do it. And other ways probably more manual because the thing with this service is that it simplifies a lot of the stuff, and you can have like an academic license to do some stuff, which is quite good. So that's an advantage. You don't have to pay for the full service. You can do the academic license. And then there are algorithms that are actually specifically programmed or coded to do that, to do this kind of analysis of how the model behaves. Particularly, there have been a few for convolutional neural networks that we are starting to see. Well, that we have started studying in the class. In general, what these algorithms do is to analyze how the gradient back propagates through the model. And then what you try to do is to analyze how this gradient is back propagated through the units in the different networks, and how the units in the different layers, and how the units or the neurons in these layers activate to certain input. And then you can have nice diagrams that show activations and how the neurons are reacting to certain input. Also, you can see like analysis of what is like the optimal input to maximize the output of a given neuron, for instance. Some techniques for this are called GradCam. GradCam is one. There is also occlusion analysis. Those two are two of the most common techniques to analyze how the network is behaving. And those are the methods that I'm aware of, that I can think of right now to analyze how the network is reacting to certain input. Is this more or less to a question? Like, because you asked particularly weight and biases, but
Yeah, well, because I was wondering if there is like a way to improve the initialization of these values.
okay. Okay. I'm answering then a different question, because I'm answering ways to analyze how the network is behaving once trained. Initializing a network is also something that is really important. I think next week there is going to be some tutorials on that. Initially, sorry for that. Let me close the door. I got. Sorry, my dog was barking and spoiling. So normally you start your training process and you start with randomized weights. In case you are starting from scratch, you are starting to train your model from scratch, you start from random weights. Having said that, you almost never do that, because in real applications, starting from scratch might not be optimal. It depends. I mean, if you have a lot of data, like LLMs, these large language models, if you have lots of data and you have lots of training power, then probably it is convenient to start from scratch, right? And everything is from scratch. In more general applications, initializing the weights of a neural network is in itself something really important. There are techniques that there is a tutorial next week, I think, which is like Kaiming-Hay is right now the most common initialization protocol to initialize the weights. It's still random, but what it's trying to do is like a more optimal technique to initialize the weights, so that the variance in the activations of the different layers are still like variance one, the distribution of the activations in the different layers are still like unit variance and mean zero, so that there is still noise in the activations. Because if you initialize the random weight, the weights just like randomly, you will see that they collapse to zero, and then you have like the latest layers in a network will have a total collapse. I mean, no variability in the weights, in the activations of a given layer, particularly when it is deep. So initializing the weights is really important. Kaiming-Hay is the most commonly used way to initialize the weights right now. And it's basically random, but it divides by the square root of the number of the inputs to that particular layer, and it works really nicely. There is variations. I mean, Kai-Ming He is the most commonly used when you are using ReLU activation functions. That's why Kai-Ming He became really popular, because there was, prior to Kai-Ming He, there is some initialization called Glorot, which is basically the same, but Kai-Ming He did a little bit of a change because of converting the negative values to zero. In expectation, the variance of the activations would be divided by half, because you wouldn't have negative values. So you would have like the distribution would be like flattened because of non-negative values. And so to compensate for that, they just multiply by 2, and it worked nicely. But yeah, there's going to be a tutorial for that. Kai-Ming He, I think, right now is the most common one used. But it's a really good point and really tricky. And probably one of the reasons of why neural networks got to train and achieve better results in the late years, like within the last 10 years, I would say, which is nice. By the way, Kai-Ming He, I don't know, have you seen the video on ResNet this week? I think it was this week.
I have not.
Not
Pardon?
yet.
No, well, doesn't matter. I just wanted to say ResNet, which is one of the most popular convolutional neural networks available, the residual network. It was the winner of the ImageNet competition in 2015, and probably the last one, because that was the one that had a result that was by then better than the human standard, like that 5% mark. So the error was like 3 point something. I don't remember exactly what's the decimal number, but so it was a very small error. And so this paper was presented by Kai-Ming He. He was a researcher at Microsoft back then. I think now he works in Meta. But still, I mean, that was a breakthrough in a model. And in that same conference, like, I think for that same paper model, they presented the initialization called Kai-Ming He. Well, it's called because of him. So it was like two of the most remarkable contributions to training neural networks and to neural networks, particularly in this case, convolutional neural networks, like by the same author in the same conference, which is remarkable. Yeah, so the Kai-Ming He initialization and the ResNet were I don't think he called Kai-Ming He initialization the way he initialized the parameters, but still, yeah. It would be very weird that someone calls something after his own name, like yeah, that would be, yeah, weird. Like even Alan Turing didn't call the Turing machine the Turing machine. So hopefully that's. No, but this is a really good point, how to initialize the weights of the model. The other thing that I was saying about weight and biases is a really good way to program how to train your model like to do different runnings of trying different hyperparameters. And the other thing I said is how to analyze the behavior of the network. Okay.
Thank you, Professor.
No, thank you for the question. Sorry for the long answer. Yeah, is there any other question that you would like to? So, okay. What we have been doing, like the videos were available since last week and also this week, convolutional neural networks. Convolutional neural networks are I would argue that are the most successful models in deep learning, and they are the models that actually brought back the neural network into the eye of the scientific community. And eventually that led to the moment we are living today. Probably, arguably, we can say that now is the transformer model, even more successful than the CNN, than the convolutional neural network, particularly because of large language models and all these, LLMs that we have. So, but prior to the transformer and ChatGPT and all these, CNNs definitely have had a lot of success. And I would say that even today, they are quite useful and really a strong model for many applications that have to do with image classification. And image classification is a really important task because all this anomaly detection in manufacturing process, well, that's image classification. That's why I believe the convolutional neural network is a really important model. And still in recent models, like for instance, now that we have diffusion models, like the models behind Stable Diffusion or DALI that draw these pretty pictures of whatever we say, like, well, whatever is that you're a pretty dog playing hockey, and then you get the doggy playing hockey. I mean, they are based on diffusion models. Well, some of them, most of them. And diffusion models use convolutional neural networks in the process of generating the image. So what I want to do today is like go very briefly through this paper, because right now, this is a paper from a previous student, master's student. This is his thesis work from Vicente. He graduated in 2022. But I find this paper really interesting in the point of view that there is not a new model in this paper, but what we present in this paper, and particularly Vicente did, was a lot of experimentation using different variations of the data with different sets of combinations of mainly convolutional neural networks. There's also some other other networks. Probably we should have said neural networks only because it's not only convolutional neural networks, but still he tested a lot of variations in the CNNs. And I think that's kind of interesting. And so I want to explain a little bit of the paper because I think by now this paper summarizes, or is an application of the things that we have seen so far, except for the last part of those recurrent neural networks that we are still going to see in a couple of weeks, I think, in 3 weeks, I think. But still, I think most of it, apart from that, is totally understandable, and it summarizes what we have seen with something that I consider a nice application. So this is also to do with my area of research. So just to put it into context, to put the problem in context. So it says motor imagery. Motor imagery refers to imagining, using our imagination to pretend we are moving some limb or some arm, leg, whatever. So if I told you to imagine that you are moving your arm, that would be motor imagery, right? So you're trying to activate some motor activity using your imagination. And so it's analyzing this kind of response using EEG data, electroencephalogram data, with convolutional neural networks. And the typical application for this is brain-computer interfaces, BCIs. There is open data sets. There are many open data sets for brain-computer interfaces experiments. And the idea is that if you plug someone electrodes in their heads, and then you tell them, okay, imagine that you are moving your right arm in a certain way, and you then get those signals from the electrodes, and you analyze them using some sort of computational model, in this case, convolutional neural networks, machine learning, whatever, in this case, particularly is convolutional neural networks. You should be able, at least that's the hypothesis, that to recognize the movement. And the applications for this, well, they range from a variety of applications, but the main application, or the one that people are trying to work the most with, is for people who don't have limbs, right? Trying to have a robotic arm or something like that. So that's the application for this. Well, one of the applications. Other applications is biometrics. Biometrics also is something that potentially can work using brain analysis. Ideally, or not ideally, but the hypothesis is that also our brain signals are unique. And so we should be able to do recognition of the person, identification of a person via brain signals. That's a little bit more tricky because your brain signals might change along the day. So even if you manage to implement a model that is recognizing very well a person for a certain amount of time, probably if the next day you don't sleep well, that very same night you don't have a good night's sleep, then next day you wake up and do the same model that was already working the day before, it might be the case that it's not working anymore because your brain signals have changed. So it's very tricky to do human identification or biometrics. But in this case, okay, the problem is motor imagery. That's kind of more studied, along with some other kind of applications with EEGs. So that's the setup of the problem. And the idea is, well, one of the ideas is motor skill impairment, where I was telling you, I mean, people who either don't have a limb or cannot move a limb. Also, it's tricky, but this is important because experimentation might fail, because when you do motor imagery with people who actually have the limbs, like if I try to imagine to move my arm, my imagination is not going to be as good, let's call it like that, good, quote unquote, as someone who actually don't have limb. And kind of makes sense because I do have limbs, so I can move it. And someone who doesn't have it, sorry, might actually, I don't know, send a more accurate signal of how the actual movement is. Okay, so that's the problem. And what was very interesting in this research, as I said at the beginning, is that there was a lot of analysis in 1D, 2D, and 3D variations of the data, and then several variations on convolutional neural networks, and variations in the representation of the data. So what I want to mention now, this is how the electrodes are placed in the head. So this is the nose. Imagine that you are looking at the head from above. And this is just a diagram of how the different electrodes are placed. This is a standard placement of the electrodes. And every abbreviation you see is just the standard notation for the electrodes. So that would be the F for the frontal lobe, T for temporal lobe, O for occipital. The occipital part is this is interesting. This is the part of the vision cortex. So this is the part that activates the most when you are actually looking at something. Interestingly, and this is also kind of interesting, well, at least for me, is that when you are dreaming, this part of the brain activates. When you're sleeping but dreaming, so sorry, the occipital part, this part of the brain, the back of your head. And this is the part where there are these kind of particular areas where there is an area called the FFA, the fusiform face area, and there is also the fusiform face area is the area that activates when you see faces. I mean, it's really interesting because that area of the brain, it activates for many things. When you might be looking at an object and it activates, but if you see a face, it actually activates a lot. So it's definitely for that. And there is the parahippocampal, I cannot say it, parahippocampal place area. It's the PPA, I will call it PPA, which is an area also that activates when you see places, which is also interesting because there are experiments that you see, I mean, it reacts to places, specifically to places. It's kind of interesting. Well, that's in this part, in the back of the brain, right? A little bit deep inside the brain, but still at the back, occipital part. And so depending on the area, the electrodes have different naming convention. So you might have different parts. Right? Now, having said that, the motor part of the brain is this part, like if you have the, I forgot the name of this gyrus, the central gyrus. So you have the central gyrus, which kind of runs in the middle of the brain. And so just in front of it, you will have the motor part, I mean, the part of the brain that reacts to motor activity. So that would be more or less in this part. So which is the part that has the most activation when having motor activity. So this would be the part that, at least in theory, the hypothesis would be that this is the part that activates the most when you are actually moving. That has to do with movement, particularly just this part here would be, at least in theory. Now, having said that, this is how you place the brains, the electrodes. The electrodes will measure the aggregate electrical activity of these pyramidal neurons that are here in the cortex, that we have in the cortex. So they will measure that kind of combined activity. And so the problem here is that even if I place, say that we are talking about this this electrode, F7, right? In this case, we have 64 electrodes, but I mean, we have many more neurons, right? So EEGs are very attractive because they are non-invasive. They have very good temporal resolution. They react very fastly. But this electrode is going to be measuring activity from a lot of this area, like what the activity, the voltage level that we're going to measure here is not like from the neurons exactly behind the electrode, but is the aggregate of all this area, right? So that's why they are not very good at spatial resolution, but still, at least the research is okay. Let's try to make the most of them. Like they are a really good tool for neurologists because they are very cheap to. I mean, it's really easy to measure someone with an EEG, right? Because you don't have to. First of all, is way more or less expensive than something like an fMRI, like a functional magnetic resonance imaging, and you don't have to take like a liquid contrast liquid and things like that. Yes, question, Daniel.
Yeah, I was thinking about something. Does the F7 dot and the F5 dot, like, do they gather information, like the information that they gather is quite different? I mean, at the
No.
level that it's really difficult to perform a PCA that try to like do a generalization of the information of some dots that are like close to each other?
No, the information, the issue is like, okay, let me show you. Like, this is the way. This is an actual EEG. This is how the information looks, and this is an actual EEG. Like you will have 64 channels, but this is the first channel, this is the second channel, and so on. So it's really difficult to know what's going on because they look very much the same. So, I mean, people sometimes do some sort of pre-processing, not so much as PCA. And so pre-processing mainly involves like removing certain frequencies because that's another issue. I mean, in the end of the day, every electrode may behave a little bit like an antenna. So definitely they are going to catch like frequencies from the electricity line. So there will be always noise in the 60 hertz area frequency. And the brain signals are between low frequencies, probably up to 50 hertz. No, 40 hertz, I would say. 45 hertz, something like that. So sometimes what you do is to remove these noisy frequencies. Also, because in the end of the day, if you place the electrode not in the brain, but say in the forehead, you might have activity from the muscles, right? And you might record the signals coming from the muscles, not the brain. So you might have also noise coming from the muscles that you have on the face. So the signals look very, very much similar. Every channel will look, if you look at it, unless you're like an expert, like a doctor that actually knows what you're looking at. For instance, if you're evaluating patients with epilepsy, you might have something that is actually characteristic of the person, but still is not like, it's not very, I mean, it's not easy to distinguish between electrodes because
And is
again,
it common to use like Fourier analysis to take out the noise of the series?
it's common to use Fourier analysis. Yeah. I mean, Fourier definitely is still used in analyzing the signals, but still, you can use Fourier like to analyze the frequencies. But this is also something that you know. I mean, if you see 60 hertz, well, 60 hertz, is not from the brain. Is mainly from the electricity line. 50 hertz in Europe, also same thing. So that's why you sometimes just apply the filter, like notch filters. I mean, like these very specific filters, or you first of all low pass filter the signal so that you got everything, say from, I don't know, I would say some 70, 80 hertz, and then you notch filter the 60 hertz. But Fourier is not that common. I mean, to analyze the signal, to apply the filters, not necessarily, because you can apply the filters directly to the signal. The hypothesis we are following in this research is that the fact that we are using deep learning and neural networks should, at least in theory, allow the model to learn to isolate and remove all the signals that are not coming from the brain. Like one of the advantages of deep learning is that it's end-to-end. And so at least in theory, we hypothesized for this work that the model should be capable of removing all the noise, just to learn to ignore the noise, like for instance, 60 hertz. So in this research, we didn't do any kind of pre-processing to remove anything. We didn't do anything like that. So it was all the signal as it was coming from the measurements. We use an open data set called BCI. Well, there are many from the BCI data set. There are many different experiments, and we use one of those. And so, but yeah, Fourier is commonly used to at least to analyze the frequency content in the signals. Absolutely.
Thank you.
Thanks for the question. Really good questions. So let me see. Okay, this is what I want to show. Just to show the data set that we were using is, as I said, one data set from BCI, brain computer interface data set. And what I wanted to mention is that this is the experiment of how the data was acquired. So you would have a baseline. The baseline is just like a rest period where you want the person not to be doing anything so that you can have like your zero, your reference level, if you want to think it like that. So you have a baseline with open eyes, same with closed eyes. And then is when you have the tasks, which is motor execution, like imagining, task 1 and 2 is actually moving the hand. So, 1 and 3 is moving the hand. 2 and 4 is imagining moving the hand. So, and then you repeat that pattern. 1, 2, 3, 4, 1, 2, 3, 4. Those are the recordings that we are using. And so the problem, we focus on doing 3 tasks. And this was just classifying task 0 and 1. Let me just have, I remember this. There were 3 classes. T0, T1, and so that would be rest, that would be task 0, that would be task 1 and task 2. So that would be distinguishing between resting, imagining, or actually moving the limb. That's how we set up the problem. We ignore the other measurements. And the problem was basically classifying these 3 tasks. So it's a simple classification problem. This is a little bit of how the data was split. I don't want to spend a lot of time here because it's just how we split data. When you're working with, in the end of the day, this kind of EEG signal is a time series. So it's a signal that is changing with time. And we have voltage levels. That doesn't matter if it's voltage or if it is some other kind of unit. But you have a signal that is varying in time. So what we did for this experiment is like intervals of 16 seconds. I think that has to do with the duration of every task here, if I'm not wrong, had a duration of 4 seconds, if I'm not wrong. So in 16 seconds, you have these 4 tasks. So you have 2 resting periods. You have task 1 and task 2. Every one of them is 4 seconds. So the first experiment, and there were many experiments, and that's what I like about this work, is that the experimentation was quite extensive. And so there is a technique to convert these signals, this time-varying signal, into an image. So what we are doing is a spectrogram. Let me see if there is a bigger picture of a spectrogram here. No. So what you do, basically, what a spectrogram does is to represent in a picture the frequency content of that signal and how it is varying with time. So let me see if I can do this bigger. Probably change the color. So this would be a spectrogram, right? And so this image that looks like a color map, what this means is that this is the time and this is the frequency. So lower frequencies are at the low part of the image and higher frequencies are at the higher part of the image. And then this is time. So this red indicates, for instance, low frequencies. but quite active. And then this one here would be that high frequencies are not that active. And in general, you will see that the reds, the low frequencies are much more active than the high frequencies. Is that clear? Like the spectrogram? Cool.
Can you repeat that, please?
Yeah, absolutely. Let me see if I can probably find a better picture online. Let me see if I can show spectrogram. Let me show probably, yeah.
So it means kind of if the region is more lit, it has more activity in those frequencies.
Yeah, exactly. Yeah, let me see. Because all these are spectrograms. Let me see if I can show. Well, this could be. I mean, it's not exactly the same, but I can use it just to show. And I probably will do annotate here. So this part here, this would be the time, right? This is time, and this is the frequency. So you will see that these are low frequencies, and as you go up in the image, is high frequencies. And then is how it is varying in time. The red colors indicate high activity. The blue colors indicate low activity. So if we had the scale, it would be like reds at the top, and then all the way till blues. Probably we should have incorporated this kind of color bar. But still, so in this spectrogram, for instance, you can see that. So this is time, right? This is the duration in seconds. I don't know what's, I cannot see, but it's probably less than a second. Probably this is one. So it would be like, okay, in the low frequencies, like this is 0.2 seconds, and this is frequencies less than 1 kilohertz. So this is quite active, right? And you see that in general here, low frequencies have more activity than what high frequencies have, right? At the top, you have high frequencies. So the reds are more active. So going back to, so in these spectrograms, it would be the same, right? Like the reds indicate low frequencies with a lot of activity, and then you have higher frequencies with no activity. And this is how this is 4 seconds duration. So this would be the duration in time. Is that okay?
Yes, okay.
Yes.
And so what we were doing here is that, okay, this little bit of, for every chunk of 4 seconds, like this would be 4 seconds of the signal T1, we generated a spectrogram, and that would be this first spectrogram, okay? Then for these 4 seconds, which is this part here, this part of the signal, there was another spectrogram, and so on for all the 64 signals. So for every channel, because you have 64 electrodes, for every channel, there was a spectrogram generated. And so you have this kind of volume of spectrograms, right? So you have 64 spectrograms per interval. Now, once you convert a signal, this is very common in audio as well. I mean, this is common in when analyzing brain signals, also very common in audio because you also have time-varying signals. And the idea is that you can see how, with a picture, you can see how the frequency contents of the signal behave. That's the idea. And so we generated 64 spectrograms per sample. This was just the measurement of. And then we, or the spectrum. Yes, please, question.
Is there any assumption of the way that these time series must behave before running this type of models? Or you can run this with a time series data, however it is?
Time series data what? I didn't hear the last part.
Like however it is, or despite any kind of feature. I mean, in classical models, sometimes you need to know that the time series is like stationary or stuff like that. In this case, it can be like any type of time series, right?
In this case, for the particular experiments we were doing using neural networks, we know that the signal is varying with time, right? The signal is varying. It's going to be like this. whatever it is going to be varying in time. And our hypothesis is that since we are using neural networks should be able to take the data, the raw data as it comes, and they should be capable of learning what's important from that signal. That was our assumption. And for now, the way we set up the problem was classifying if the signal was representing rest, was representing actual movement, or it was representing imagery. And that's it. And we didn't do anything else. I mean, we didn't take into consideration any additional information from the data. Just the data as it was coming from the brain, well, as it was coming from the data set, but the data set is as it came from the recording of the person. So that way it entered the model like that. No additional pre-processing or anything was done on the data.
Yeah, I mean, I asked this because I just have a question. Because once I had to run a model to identify if someone, like a consumer, was committing fraud on the consumption of a specific service. So it was a problem, like, was quite similar. Like, I mean, you had like a time series of consumption of service, and that time series was related with being committing fraud or not. And I was just thinking that that kind of structure of a problem can be applied with this kind of techniques, like just taking into account that you have a time series that have a classification, and you can run these kind of techniques in order to do that type of classification.
I think it's quite possible. Yeah.
Okay. Yeah, well, that was like my question.
Yeah, I think it's possible. I mean, still, sometimes when you have this kind of noisy signals, because it's kind of difficult to even for a model, a deep learning model, neural network, not always is it possible to recognize what the data is representing. So, and in those cases, and even when we hypothesize that not doing any sort of preprocessing was required, I think we could have achieved better results if some slight preprocessing would have been carried on the data. And then whatever you do in time series, I mean, depending on the data, if the data you have is like this, then probably you can just treat it as a signal and put it into the model. But if you have like more like tabular data that is kind of, well, in the end of the day, this is tabular data, but what I'm trying to say is that depending on the problem, it might not work. I mean, in this case, it worked nicely, but in your case, I'm not totally sure, but it might. I mean, at least in theory, you could try something like this, particularly 1D convolutional neural networks. Those led to very good results, at least in this problem. Yeah.
Okay, thank you.
Yeah, no, thanks for the questions. Any other question, Adriana? I see the hand.
Yes, thank you. It was kind of a similar question that about what drove your decision of transforming those data points into images and why to process images. But it's what you said. Or maybe I was thinking that maybe sometimes we should try different models to see what we get with data of.
Absolutely. Yeah, absolutely. And that's what we did in this. Well, mainly the P-Center was the one doing all the experiments in this work. It is very common to analyze signals as images. And that's why there are many algorithms that will allow to convert the signals, time-varying signals, to images, like in this case, spectrograms, and there are power spectral density functions and things like that. I think they show a lot of information. So if any way they are going to be transformed to images, then we have seen that convolutional neural networks work very nicely with images. Okay, is it possible that converting to images leads to better results than working on the data itself as it comes? That was the motivation behind doing this kind of experiment. But as we will see in a few pages, that was not the only experiment. And even when these led to really good results, the limitation here is that converting to images was very expensive. I mean, it took a lot of time generating every spectrogram. So that was computationally was not feasible, because this wouldn't be able to run in real time like Eva, because generating every spectrogram is too computationally intensive.
Okay.
More
Thank you.
than more than doing an inference with the model, way more. So even with the results were very nice with this approach, computationally they don't make a lot of sense. But still, the tool is it is common to convert to images and analyze images even from data that didn't come originally as an image.
Okay.
Yeah.
Thanks.
Yeah. Good question. Thank you. Abel, yeah.
So this is like a silly question, but thinking about normalization, so even using images prior to input the information in the model, should we apply any normalization like min max to the pixels or something like this?
When we are doing, normalization is always a good practice. In the end of the day, particularly when you are working with the data like this, normalization might not make a lot of difference because the values are very close together. So you normalize the idea of normalization, at least the like the more general reason that you are doing normalization is to bring all the values to the same level. Once you have them in the same level, for instance, if you do min max or if you do set score normalization, that you bring them to a mean of 0 and standard deviation of 1, what you will have is that the value are closer together. And that is good because you will allow the model not to pay special attention to the larger values. Also, the training will be faster. That's a fact. So in the case of these signals, normalization was not used because they were already in the, were very, very close together. We could use it and wouldn't change much. In the case of the images, normalization was applied. Because if we have pixels here that we have values from 0 to 255 to say something, then we want to bring them to values that are closer together. So most likely 1 to 0, 1 from 0. And also we want to use floating points. That's quite important for when working with images.
Thank you.
So yeah, normalization is always a good idea. Yes, Juan?
Hi, can you hear me?
Yes.
Okay, I have a question about the image that you are showing us, and is why did you choose 4 seconds? I mean to split the waves.
The 4 seconds is because that is the duration of the experiments in the data set. So when I was showing these tasks, the duration of every task here is 4 seconds. So in this case, it's like 4 seconds with your eyes open, 4 seconds with your eyes closed, 4 seconds actually moving your arm, 4 seconds imagining that you are moving your arm, and so on. That's why 4 seconds is like the label of the data, the duration of the activity of the task. So in order to label the data, we use that. So if this is the continuous signal, so splitting them in 4 seconds would allow us to say, okay, all this activity, all this data corresponds to the 4 seconds that the person was resting, or T1, I don't know what is task 1. Motor execution with one hand, right? That's why it's 4 seconds, because that's the way the data comes.
Okay, thank you. And another question,
Yeah.
could you recommend me a website or something like that to download free or open medical data sets like this one?
Yeah, I think it depends on the kind of data set, but medical data sets are probably the domain of data that you usually don't struggle to find, because there are many. And my advice would be, depending on what kind of data there is, I don't remember exactly the websites, but if you look for it in Google, you will find them. Like there is one for cancer that has scannings and data of a lot of different types of cancer. There is one, how is it called? NEAT? I forgot the name, but has to do with brain scannings. This was the BCI dataset, which is for brain-computer interface. For medical applications, there are a few available. There are some that are for malls, like also in Kaggle, you might find some data sets that are for medical applications. So depending on what you are looking for, I would say that if you Google, I mean, after 20, 30 minutes, I guarantee that you're going to find some good data for many problems, for medical applications, at least. And they are usually like nicely treated, like anonymized, and they usually include how you can use the data and so on. So, but medical application, there are a few data sets like I don't remember from the top of my head the name of the data sets, but if you Google it, you will find them. They are not that difficult to find.
Thank you.
No, thank you. Okay, so that was the way we did, and in this case, the spectrograms. Oh, sorry, this is what I want to say. The spectrograms, these little squares, these spectrograms, were of size an image of 32 times 32. Okay. So yeah, that's what I want to mention. And so in this case, you have this 32 times 32. Since you have color, then you have an RGB picture per spectrogram, and then you have 64 channels. So you have a stack of spectrograms. So you have a volume, kind of an activation volume, but in this case, it's like an activation spectrogram because we are going to use it as an input image. The only difference is that if in a convolutional neural network, you use, say that you have an image that is, sorry, 32 times 32 times 3, because it's RGB, well, and you pass it through the network, nothing is preventing you from having something that is 32 times 32 times 64, right? You can have a very big volume. That was an experiment that was going to be carried out. Now, some other arrangements, okay. I'm just talking about the setup of the experiments. Another way to do it was like, okay, we generate an spectrogram for each channel, like this, and for each like 4 seconds duration as well. And then we stack them all together. Rather than having a volume of spectrograms, we stack them together in a 2D image, like this. So this would be the spectrogram for the channel 0, channel 1, and so on for all the channels. And then we stack them together in as a single image. And then this becomes a new image to the model. And for this, also something that we tested, in this case, it was all the 64 channels. That was computationally very expensive to do. So in sequent experiments, we were limiting the information to the motor cortex, to those electrodes that are in this kind of area, in this area here that corresponds, that is expected to be the most affected by motor activity. So in order to make the experiments more efficient. It doesn't mean that this electrode, for instance, is not going to record some activity when you are moving something, but most of the activity is expected to come from the motor area, which is this part of the brain, this kind of where my headphones are sitting, kind of this part of the brain. So that was another way to modify the data. And then something that this experiment was done with different setups of electrodes. And so we repeated that for 21 electrodes, 13 electrodes, which was this part here, those in blue, then only 9 electrodes, which there might be a diagram here, which was these electrodes here in this area. And then there was one with 5 electrodes, if I'm not totally wrong. I'm gonna be skipping that. Okay, another experiment was, okay, we take the electrodes. I mean, this would be 640 samples because that would be the number, the frequency, if I'm not wrong, the sampling frequency of the EEGs was 256, if I'm not wrong. I can recall that from memory. 256. No, it must be. Let me have a look. For 600, that would be. I can recall the sampling frequency. But what I'm talking about is that for every time you're sampling a signal, you will have certain number of samples per second, right? So in the case of EEGs, frequencies like the highest frequency rates that you will see is like 512. That would mean acquiring in a second 512 samples. I think in this case it was less than that, but that's what I was trying to do. But we can calculate it here. If it was 640, then we had 320 because it's 4 seconds. So that would be 640 divided by 4, and that would be the sampling frequency, right? So that would be 160. So the frequency sample for this EEG was, recall that this represents 4 seconds. So it would be 640 divided by 4, 160. So that would be the sampling frequency of the EEG. Well, what I'm saying is that then 21 channels were taken, and then you have all the channels and this duration. And then instead of rearranging this in spectrograms or something, these were rearranged in this kind of three-dimensional array. So the duration would be still 640, but then this 21, you would split this in 7 sections and then combine them. It was, sorry, 3 channels. 3 channels were taken like here, the whole 3 channels, and then we put them together in a stack, like if it was a 3-dimensional array. Right? So it was only a way to rearrange this data. This is a matrix in the end of the day. So it was a way to reshape, if you think in terms of Python, it was a way to reshape or permute this array to have it like a volume. Why? Because we want to say, okay, let's try to do this 3D kind of volume and pass it through a convolutional neural network. Now, the convolutional neural network would have 7 channels in its input, not only 3. It wouldn't be like RGB. This would be 7 channels. Does this make sense? And in the end, I repeat, it was just testing what's the best way, what kind of variation and manipulation on the data works better. And that's what I like, because this was a lot of hard work in sense of transforming the data and then running models. So yeah, I'm going a little bit fast. This was repeated for several number of electrodes or channels. So let me do this was the same for 5 channels. But what I want to do is let me see, because this is already the models. No, okay, I'm missing something, which is before the models, something that I wanted to mention. This was the last experiments. I mean, so the first experiments were converted into electroencephalograms, both in this big volume that was the most expensive computationally, then the vertical stacks with also electroencephalograms, and then this volume representation that I just showed for different number of channels. Right? So far it's 3 types of transformations. And then the final kind of experiment was actually taking the data as it comes. Okay, let's not transform it into anything. Let's just take the data as it comes. It was a single channel arrays of the raw EEG data. That is the data. Oops, what did I do here? Oh, what happened? I think, I know what happened. It crashed. Sorry, was there a question? Yeah, it crashed. Let me open it again. Yeah, my application crashed, that's why. Let's see if I can. What is this? And open up, the file cancel. Restore file. Okay, here it is. So the last experiment was actually taking the data as it comes, this kind of data, and pass it through a model. Okay. So now, okay, this is the setup of the data, the different kind of arrangements in the data, transformations to the shape of the input data, and then come the models. Where are they? And so the first model was a very simple convolutional neural network. This kind of convolutional neural network, where the input was the spectrogram, the kind of a spectrogram that we talked at the beginning. And also this 2D matrix, which was the spectrogram. Okay, this is the spectrogram with the 64 channels. This is the 2D matrix coming from the spectrogram of the image with the spectrograms stacked together vertically. And this input was the data transformed into this kind of three-dimensional array, right? This kind of transformation. So for all those variations of data, we use convolutional neural networks. The only thing that we needed to change was the number of channels to the input. So this was like with 64 channels, kernels of 3 by 3, stride of 1, padding of 1. So very simple model, just like the most simple convolutional neural network you can think of, only one layer. So followed by ReLU, then max pooling, then a linear layer that will allow us to have the number of classes. So this would have like three neurons, and then the classification. Okay, that was one model. So we repeated everything, the same data, but now with 2 layers. Okay, not a lot here. What about having 3 layers? Same data, now let's do it with 3 layers. And the last part of the convolutional neural network experimentation was using now a pre-trained model. And I was talking about ResNet. ResNet, as I said, was this model that won the ImageNet competition in 2015. And so the idea here, and this is something that I don't remember if the videos of this week include was it this one? Transfer. Okay, it's called, anyway, it's transfer learning. What we are doing is that what we are having is a model that was pre-trained on some other data is used now, and we do kind of a domain transfer so that that model can be used for another application. So what we are doing here is that we are taking a model pre-trained on ImageNet. So this model already have knowledge of how to recognize certain kind of images. And then what we are doing, okay, taking this pre-trained model, and then we pass it through a 2D, a 1-layer convolutional neural network, and then a linear layer, and then we have the classification. So just to make because this is transfer learning is really important in the context of neural deep learning, because what you're doing basically is like for instance, right now you're looking at images of spectrograms, and maybe you have never seen spectrograms before, right? But still, you see the image and you can recognize characteristics in the image. You could, for instance, say, okay, there are some colors, there are some signals, some lines, there is some structure in the data. Why? Because you have been pre-trained with many images before, right? You already have knowledge of what the world looks like, so that you can transfer that knowledge to some sort of other domain. Even if you see, like, for instance, medical data that you have never seen before, you would be able to describe the data. There are shapes, there are colors, there are textures. That's the principle in transfer learning. Take a model that was pre-trained, usually ImageNet, and then use it so that you can train a model that doesn't have to be that big. And transfer learning allows to achieve very good results with little data, not so many images, and then also with not so big models, because we are using all that knowledge that someone else trained. I mean, probably ResNet was trained for 2 weeks in 8 GPUs. So already that model is already available, so we can use it and deploy it for our own applications. And if you're using PyTorch or whatever you're using, like PyTorch, TensorFlow, they all have these pre-trained models, which is basically the same principle as if you download Llama and then you fine-tune Llama in your own application for your own problem. So it's basically the same principle. In this case, it's only for images, and it was probably the first very well-known application of transfer learning. So given that ImageNet images are 224 times 224, the spectrograms were transformed to this size, then passed through ResNet, then a one-layer convolutional neural network, and then the classification, and the same process was done with the 3-layer convolutional neural network, right? So this was the model that we trained here. This model was placed like on top of this pre-trained model. And the idea of transfer learning is that now, instead of training the whole model, you are just going to focus on this part. You are going to adjust the parameters for this part. Yep. Okay, and there's a tutorial for that. So I'll explain that. You will get to practice a lot with transfer learning. And so, okay, but when we have the array data, the one that is the spectrogram, the stack spectrogram, so also we can pass it through a convolutional neural network. Oh, sorry, no, this is not all those models were for this kind of multidimensional array kind of image. And now the last model was a 1D convolutional neural network. And this one-dimensional convolutional neural network was taking the raw data as it comes. The 4 seconds of data, 640 numbers, were passed through a convolutional neural network. But in this case, it's only a 1D convolutional neural network. So the convolution kernel, rather than being, for example, 3 times 3 in an image convolution, it would be 1 times 3, right? That would be a 1D convolutional neural network. Principle is the same. So we pass it through this one. Okay, and then 2 layers, and then 3 layers, but this is still 1D convolutional neural networks. 4 layers as well. Okay, there were a few. There was a 5-layer. I didn't remember this, that there was a 5-layer convolutional neural network. Okay, and so everything was trained. These were relatively simple models to train. And so what I want to show is now the results, just quickly. Because, and actually, yeah, I'm looking at, in this paper, we didn't publish anything about recurrent neural networks. That was in Vicente's thesis that we did it. By the time we published this paper, he hadn't yet done the other experimentation, which is the reason why it is okay to call them CNNs. Okay, anyway. So these diagrams, what these diagrams show is the dotted lines, these purple and these like magenta lines, are what by 2020 and 2018 were kind of the state of the art for this data set, because it is a common data set, so it's not like we were inventing this problem, but this was like the best models in the state of the art, right? And so what we are showing is different arranges, different setups of experimentation. So this is a state of the art, the best results in the literature, these two results, the dotted purple and the dotted magenta. And so what we have here is the single layer convolutional neural network. And these are the results for the different number of channels. So these were the vertically stacked spectrograms with one single layer convolutional neural network, 2 layers, 3 layers, and the pre-trained ResNet. The number 18 means that is ResNet, the version with 18 layers. The biggest version of ResNet is 152, if I'm not wrong. And there might be some other bigger, but the ImageNet competition was won by a ResNet 152 layers. So another ResNet. And so what we're showing here, okay, all these results are the ones coming here, right? The vertically stacked spectrograms. So we can see that this is one single layer convolutional neural network, really poor. All the results are bad. 2 layers, this model, which is the results for the single channel spectrogram, This is the spectrogram, the having the 64 spectrograms stacked together in this volume, the very first experiment. Okay, that's a little bit better. With 3 layers, okay, we get a good result, more or less about the same as the state of the art. But what was remarkable, at least by then, is that the ones that we use with the pre-trained model, ResNet 18 and ResNet 18 plus 3 layers, they had really good results. I mean, they were over 90%, which was far ahead the state of the art, which was about 70%. So these two really work very well. These are the best results in all the experimentation, but they were very computationally expensive because of the conversion to the spectrogram. Yeah, transfer learning is like fine tuning. I'm looking at the question in the chat. Yeah, it's kind of a fine tuning, but before fine tuning, the term was transfer learning. Yeah. So, and I want to show the pictures because the graphs. And so this was the experimentation for the 2D matrix. Okay, this I remember. This kind of setup of rearranging the spectrograms, sorry, not the spectrograms, the raw data in different kind of multidimensional arrays. This was bad. I mean, these results are really, none of them are, I mean, this one is like better than the state of the art, but I would believe that might be, I mean, maybe this is the sweet spot in the number of channels, because something that is interesting is that 64 channels, even with 3 layers, behaves way worse than the state of the art. And so it seems that 9 channels with only 2 layers behaves probably better, but still in general, doing this kind of stacking, not stacking, doing this kind of rearranging the signals in this kind of weird multidimensional arrays is this experiment. Let me show you the picture just to wanted to open the navigation panel, but just to recall, it was particularly this kind of rearrangement, what I'm showing right now. This kind of rearrangement is still the raw data, not converting to spectrograms, but passing it through a convolutional neural network. And then we see that the results, is these results. The results are not that good, right? Okay. So this is the detailed results, but only this result is better than the state of the art, which is not really good. I think this is, wait, I'm now confused which 2D matrix raw EEG signal. Okay, this is not exactly what I was saying. Sorry, those results are just taking the data. I remember now. This is taking the data as it comes, like this, but then passing it through a convolutional neural network, 2D convolutional neural network. These results are the ones I just explained of rearranging the data in these 3D volumes. Also really poor results, not very good. And also it shows that 9 and 5 channels behave better than in general than 64 channels. So that's interesting. And now what I want to mention, which is probably the results I feel are the most remarkable because they are the least computationally expensive, is using just 1D convolutions. 1D convolutions is the last test we did. So the data was like this, and we took channel by channel in a 1D convolution. And then even the single layer one kind of matched the performance of this state-of-the-art paper. And then all the others, they were better than the state-of-the-art. Still not as good as the spectrograms in the first experiment, but these were just the data as it was coming. I mean, no transformation at all. And this is using 1D convolutions, which was kind of what we expected, because in the end of the day, applying 1D convolutions to one-dimensional signals is really common. I mean, that's the process of filtering signals. If you had worked with audio in the past, like removing a noise from a voice, traditional techniques prior deep learning and neural networks was using filtering. And filterings are applied via convolutions. So that's why when they say filtro, that expression, actually you're applying a filter. You're doing a convolution to remove certain characteristics of the picture in this case, or of the signal, if you're talking about a signal in 1D. So yeah, this is the result of using 1D convolutional neural networks, which is kind of nice. I mean, we were kind of happy, quite happy when we got these results for 1D, because computationally, this was the cheapest model. This is the model that can actually run real time, even in some kind of edge computing device. It might be, well, today probably all of them would run in edge computing. Back then, probably this was the one that would have been capable of running this. And so I think there's a graph with, or is it not? No, it's not in this one. Like, this would be a comparison of all the results. But we can see indeed the best results were from pre-trained model, ResNet, transfer learning, and 3-layer convolutional neural network, 93%. That was the best. But it was the most computationally expensive experiment. And then it was encouraging to see that 3 and 4 layers of 1D convolutions led to these good results, which are still better than the state of the art back then, which is remarkable. At least it was back then, right? So the idea of this research was like, okay, let's try everything that we can. And there were some experiments that we thought about testing afterwards. We did some experimentation afterwards, like with recurrent neural networks. And even after the thesis, we thought like, okay, we should have done something else that could have worked, but still, this was quite nice to get. So, but my point, rather than the application, I mean, I find the application very interesting because it's similar to what I do in research. But my point is that by now, I mean, this is already a published paper, and you should be perfectly capable of reading these kind of papers without a problem now. At least this that is based on convolutional neural networks, because there is nothing new. I mean, everything we have seen, except for probably transfer learning, which will be covered probably next week, if it's not in this material. I can't remember if it's in this week or next week. No, I think it's this week, transfer learning. So once you cover the material for this week, you will see that you have all the tools to understand something like this and implement models like this. And that's why I like CNN so much, because I think they are very, you can achieve very nice results with convolutional neural networks, even when they are not that computationally demanding compared to today's standards. And if you're using like transfer learning, yeah, you can do very nice stuff. And all the problems that have to do like anomaly identification in images is basically CNNs. And that still is really common. It's a really important application of CNNs. Is there any question? Like, basically, that's what I wanted to cover today.
No, Professor, very interesting application. I just have like something to ask.
Yeah, absolutely.
These results were, as you said, were better than the ones back then that they had before. Are these results being improved, or are these like at this moment the best achieved?
No, I'm pretty sure that there must be something better back then. Like, and I'm gonna be totally honest. I mean, we were working on a data set that was not like the newest data set available. So it was and one of the reasons was that there was a lot of research using that particular data set. But it was probably not the most challenging data set available even back then. So I'm pretty sure that there must be something better. I mean, this is something that I haven't been working since this paper. So I don't know what's the current state of the art. I'm not sure if there is a state of the art with that particular data set, because we have to match everything, like having the same data set, the same kind of experiment, so that we can compare to that. So if it's the same data set, but they do something different with that data set, we cannot compare to that. And so these papers were like the exact match of what we were doing.
Okay,
So-
and so if there is going to be like a problem that it's about the same, like this one, you can say that we can base like to get a guidance from this paper, like an input, like a first input, and then start modifying and playing and that stuff too.
Absolutely.
To resolve a problem mainly.
Yeah, absolutely. That's what you usually do. I mean, depending on what you're doing, like if you're after like solving a real problem that has to do with classification, or you actually want to replicate this and improve on this, most of the times the first step is just, okay, take something that has already been made
Okay.
and start from there. Yeah, absolutely.
Okay, good. Thank you, Professor.
No, thank you. Thanks for the question. Is there another question? So, well, if there is nothing else, thank you very much. I mean, the idea was to show that by now you are, okay, this is 2022, but still is, I find it still relevant to see the importance of CNNs. And by now, I mean, you should be perfectly, if you have a go at the paper, I mean, I'm not asking you to do it because it's not to do particularly with the class, but you should be able to read papers that have to do with convolutional neural networks, and you should be able to understand probably 50% at least. And the idea, as I said in the first class, is to get to a point to whatever paper we get to see, we can have a good understanding of what the paper is about, what the technology is about, even if we don't understand 100%, that's totally fine. Yeah. So that would be all for today. Thank you very much.
Thank you.
Thank you,
Okay.
Professor.
Thank you
Blessings.
too.
Blessings.
Thank you.
Thank you, Professor.
Thank you. Good night. Bye.